In this video, we shall look at the concept of half-life in radioactivity. In any sample of a radioactive element, the number of radioactive nuclei, let's denote it with the letter N, decreases as the nuclei decay. So if a radioactive sample contains N radioactive nuclei at some instant, the number of nuclei, delta N let's call that decay in a small time interval, say delta T, is proportional to N. So mathematically, we can write this expression in that form. We can turn this proportionality into an equation in a following manner. Delta N over delta T equals minus a lambda N, where this lambda is a constant of proportionality. This constant of proportionality, lambda, is also known as the decay constant. And as you will see, it has a unit of 1 over seconds. This negative sign signifies that N decreases with time. That is, this delta N here, the change in the number of nuclei, is negative, as it should be. We can define the magnitude of this delta N over delta T as the decay rate, or sometimes it's known as activity, of a sample. It is simply the number of decays per second. The SI unit for R is becquerel, or with abbreviation BQ. So 1 becquerel equals 1 decay per second. The other widely used unit for R is curie, with abbreviation CI, and 1 curie equals 3.7 times 10 to the power 10 decay per second, or becquerel. So that is the conversion. Now let's look at this result more closely. To get more insight into this equation, we need to rewrite this equation in a differential form. So namely dN dt equals minus a lambda N. This is an elementary differential equation which can be solved easily. So let's rewrite the term on the left hand side to be dN over N, and rearranging the other terms like that. And let's integrate both sides. Now this is a constant, it can be taken out of the integral sign. Of course, the left hand side, it's like integrating 1 over x with respect to x, and the answer is natural log of x. So you get a natural log of n. And the right hand side is minus lambda t plus an integration constant, let's call it c. We know that at t equals to 0 seconds, before all that decaying starts, the number of nuclei is n naught. So this is the original number. Substituting this information in there, we see that c equals natural log of n naught. So let's substitute that, natural log of n naught. Let's bring this term to the left. You get natural log of capital N over n naught using the rules of logarithm, and the right hand side is minus lambda t. That means n over n naught is quite simply e to the power minus lambda t, or quite simply n at any time t is n naught, the original number of nuclei, times e to the power minus lambda t. So this is the solution to this differential equation. So let's now address the question as to what is the time when the number of radioactive nuclei decreases to 1/2 the original number n naught. So the value of t when n goes from n naught to half n naught. So let's substitute that condition in this equation and assume the t when that happens is capital T. So it becomes n naught over 2 equals n naught exponent to the power minus a lambda capital T. n naught goes away. Now let's take the natural log of both sides. So natural log of half equals natural log of that is quite simply minus lambda times capital T. Now natural log of half is minus 0.693. And that equals to minus lambda times capital T. So the minus goes away, and you see the capital T is quite simply 0.693 over lambda. So this is what we call the half-life for the sample. The standard notation of writing half-life is T to the subscript half, like that. So there we have it. The time it takes for the initial number of nuclei n naught to decrease to half of that is quite simply 0.693 over the decay constant, lambda. Let's try to plot this graph with n, the y-axis, and time on the x-axis. So we know when t equals to 0, n equals to n naught. And when t is large, then n goes to 0. So what you have is an exponential graph like that. So for that reason, this decay is also known as an exponential decay. So let's say you have two graphs beginning from the same point, with the green curve representing a rapid decay compared to the white curve. Then we say the lambda, or the decay constant, associated with that green curve is greater than the decay constant of that white curve, like that. So a larger value of lambda corresponds to a rapid decay, and a small value of lambda corresponds to a slower decay. Let's look at the following problem. The half-life of a radioactive nucleus is 1.5 times 10 to the power 3 years. If a sample initially contains this much nuclei, find the initial activity in Curies and the number of nuclei remaining after 4.5 times 10 to the power 3 years. So let's look at part A, the initial activity in Curies. So we know activity is denoted by the magnitude of dN dt. So since a dN dt is minus a lambda n, activity R equals lambda n. Since we are interested in the initial activity, namely the value of R when t equals to 0, and we know at t equals to 0, n is n naught. So we are interested in the value of R when n equals to n naught, namely lambda times n naught. We know what n naught is. It is 3 times 10 to the power 16. But how do we determine this decay constant? We know the decay constant equals 0.693 over half-life. And we are given half-life in the unit of years, so let's change that in seconds. So 0.693 over 1.5 times 10 to the power 3 years. Each year contains 365 days, and in each day there are 24 hours, and in each hour there are 60 minutes, and in each minute there are 60 seconds. So that is your decay constant in the unit of 1 over seconds. And the value for lambda will turn out to be about 1.46 times 10 to the power minus 11 per second. Now let's substitute that number in this line. So you get 1.46 times 10 to the power minus 11. N naught is 3 times 10 to the power 16. That's that number right there. And that's going to give you the activity in decay per second, or becquerel. And upon doing the calculation, you get 4.38 times 10 to the power 5 becquerel. Since we know 1 curie equals 3.6 3.7 times 10 to the power 10 becquerel. This number in curie equals a 4.38 times 10 to the power 5 over 3.7 times 10 to the power 10 curie, which is 1.18 times 10 to the power minus 5 curie. And that's the answer for part A. Part B, the number of nuclei remaining after this much time. And for this we can use the exponential decay expression. We know what N0 is. N0 is 3 times 10 to the power 16 nuclei. That is the initial amount of nuclei. Now let's calculate the exponential factor. Now we can do the calculation in years. Now we know that the decay constant is 0.693 over half-life. The half-life in years is given by that number. So let's for now stick to the unit of year. So it's 1 over year. So putting that number here, 0.693 over 1.5 times 10 to the power 3, and t is given in the unit of years already. So that is just 4.5 times 10 to the power 3. So you see that this and that will give you 3, and the resulting number can be calculated easily. And the answer is about 3.8 times 10 to the power 15 nuclei. And that solves the problem. As always, thank you for watching.